This is Monday morning. Welcome back to class. Last week I gave a lecture on introduction of machine learning and reinforcement learning. At the end of last week, I was talking about the basic structure of perceptron. And today, in an hour, I'm gonna give a lecture on perceptron and Foward propagation. Probably on Wednesday, I'm gonna give you a lecture on backward propagation. In a sense, I think this week's two classes, today and Wednesday, might be the most fundamental concept of machine learning and reinforcement learning. Let me start with the basics of perceptron. As I mentioned in the previous class, perceptron is the basic building block of machine learning. So in order to be able to understand the basic principle of machine learning, and in order to use machine learning for your artificial intelligence solutions, you have to have a strong basics of perceptron. Because in machine learning network, there will be a billions perceptrons in the network. So I will spend some time to discuss this basic concept and structure of uh, perceptron. Let's assume we have an input x1, x2, x3. This could be a vector of input of neural network. The x will be input of this perceptron, and there will be a weight for each input, W1, W2, and W3. And X1, X2, and X3 will be weighted by W1, W3, and those will be added to make a sum. Those sum will be input to the activation function. And there are many different types of activation functions, but typically we will use the sigmoid function or ReLU function. Probably next week we are going to spend some time to talk about what type of activation functions we will use, and we will talk about the properties of activation function. Output of this perceptron will be represented by y. Usually it has a range from 0 to 1, especially for the case of sigmoid function. This output range of y will usually give you the probability. I think in a sense, this is one perceptron deep neural network. So the perceptron is composed of input x1, x2, x3, and weight w1, w2, w3, and activation function and output y. This is very fundamental building block of machine learning. There might be some different type of activation function, but I may consider sigmoid function One of the example of activation function is sigmoid function. Sigmoid function has an input of weighted sum that can be represented by W1 x1 plus W2 x2 plus W3 x3 plus bias. Usually, sigmoid function has a range from 0 to 1. If x is infinite, then exponential minus W1x becomes 0. If almost 0, then it will become 1. However, if x is minus infinite, this exponential function becomes infinite. So 1 divided by infinite, it becomes 0. And when this summation input of this activation function is becoming 0, usually it cross half. The slope of this activation function will be determined by W. Slope of this activation function will be determined by W, and this point will be determined by B. So by changing W and B, the shape of this activation function will be changing. So during the training process of this perceptron, you gradually change W and B to fit to the real data. That is called training process. So training process means that W and W2, W3, and B will be adjusted to fit into the real data. So that process is called forward propagation and backward propagation. Using this output, we define cost function. There are many different types of cost function, but in this moment, I will use mean square error function. So let's assume that you have a forward propagation with the input x1 and x2 and x3. You will obtain the output of this activation function. And the output of activation function will be this, and this y dash is the target value. You obtain this target value by labeling of this data. So this is target value means the real value. This y means the output of your perceptron. If they are equal to 0, that means you have a right value of W and B. That means you have accomplished the training process properly. If this if this cost function is not equal to 0, then you have to adjust this W and B. So let me summarize the first part of my lecture today. Now I want to talk about the basics of perceptron. Perceptron is the basic building of machine learning. So you have to have right idea about the perceptron. Perceptron has the input vector x1 and x2 and x3. Summation of x1 multiplied by w1, and this input will be inserted into this exponential function with bias b. So this weighted sum will be the input of this activation function, and output of this activation function for the case of sigmoid function output range will be 0 to 1. That represents the probability distribution. Usually this sigmoid function has from 0 to 1, and the slope of this perceptron activation function will be determined by W, and the biasing point will be determined by B. So during the training process, we usually adjust W and B to fit into the real data distribution. When we are optimizing W and B, we usually define the cost function. And this is the case of mean square cost function. We continue iteration of this training process until this cost function is equal to 0. That means that your output of this perceptron is equal to the target real number. The mathematical shape of this cost function is usually parabolic function, as you can see from this figure. So initially, let's assume you have y here. Actually, optimal point might be y dash. Then you change y until you reach the minimal point of the cost function. And those process, gradually you change W and B to reach this minimal point. And that process is called gradient descent. Even though I'm using this one-page slide, this describes the very basics of perceptron and the training process. In the previous page, I was talking about the basics of perceptron. Now I want to talk about the connections of this perceptron. Let's start with very simple case, which we have 3 input. Let me do it again. In this case, we have 8 perceptrons. Input has x dot, x1, x2, very simple case. And we have, this is input layer. Let's assume that we have one hidden layer. This is layer 1, this is layer 2, and this is the output layer. Here, this is very simple case. We have only 8 perceptrons. They are connected. In real case, there might be billions or billions perceptrons might be designed into a single deep neural network. But to develop a concept and structure of this perceptron, let me start with these 8 simple cases. And also we have one input layer and one hidden layer and one output layer. That means we have 3 layer structures. Usually in DNN, the number of layers could be more than 200 or thousands. Probably in the future, the number of layers could be millions. Then we might need more imaginations and computing powers. And also we assume that number of nodes in layer 1 is 3, number of nodes at layer 2 is equal to 3, number of nodes at output layer is 2. Very simple case, but it will be okay to develop the conceptual configuration of this deep neural network. If we make these layer structures and node numbers, and if they are connected, it actually becomes deep neural network. I'll say DNN, especially if the number of layer is becoming more than 200. There are not a precise definition of deep neural network, but if the number of layers is increasing, we call it that that is a deep neural network. It will be connected like that. Also, X1 will be connected to next nodes. I'd say this node is H0, H1, H2. Let's assume this is Y0, Y1. Then the weight can be represented by WOO, W10, W. So, or sometimes I make mistake. Then this will be W10. This will be sometimes I make mistake. We can assign this matrix number. There are 3 vectors, then in this case, this is input vector. This is hidden layer output vector. This is output vector. Sometimes this numbering might be a little bit difficult. Sometimes I make mistake. But what I'm trying to explain to you is that this is the basic structure of perceptron connections. Each has input layer, hidden layers, and output layer. They are connected with some weighted number. And then at each node, the input and output, and the hidden layer output can be represented by these vectors. Now, I would like to develop an equation to make a connection between input vector, hidden layer, output vector, and output vector. I'd like to make a relationship between these 3 vectors. Sorry, this is very complicated writing process, but the first message I would like to give you is that input vectors, input vectors are multiplied with the weight, and that becomes the input of activation function. And as I mentioned before, we're gonna use the sigmoid function for a while. Then the output H will be determined. So output of this hidden layer will be determined by the sigmoid function, and sigmoid function will be the summation of multiplicated summation of weighted number in a matrix and input vector. And as I mentioned before, sigmoid function looks like this. In a this is the graphical representation of perceptron connections, and this is mathematical description of a perceptron function. In a sense, in order to do this calculation in computer program, we have to be able to conduct this sigmoid function operation, this exponential function. In addition to that, we should be able to do the matrix calculation. Matrix calculation can be easily for the case of matrix multiplied by the input vector. I think this is the very simple mathematical description of perceptron, and in other words, this can be said as forward propagation. As I mentioned before, the number of this perceptron will be huge number, and also the number of hidden layer will be large. That means there will be huge number of this matrix calculation and sigmoid calculation. So in order to the fast AI machine learning algorithm in your computer, that's why you need big strong computing power and computer memory. And also this AI computer machine usually takes a lot of electrical power consumption because of that. Now, let me, even though this is a little bit tedious work, routine work, let me continue this mathematical description of perceptron connection and forward propagation. Now, I derive the second equations of this perceptron connection. Now, in the second part of this perceptron connection, I want to make a relationship between hidden layer output vector and output vector, total output vector. That also can be described by the matrix formulation using this weighted number. But in the case of this matrix, because hidden layer number is 3, 1, 2, 3, because then we have three three column, column, and we have two output vectors. That is, we have two rows. So this is this becomes a 2 by 3 matrix here. So this matrix multiplication will be the input of sigmoid function, and output will be y0 and y1. I think this is the relationship between input, hidden, output layer. And this calculation process is called forward propagation. Let me review again up to this point of the class. The perceptron is basic building block of machine learning deep neural network. And it has an input vector and weight and activation function. Usually we use the sigmoid activation function, and later we will talk about many different types of activation function, probably next week. Our output has a probability distribution, and sometimes we call it this is a classification. If you give an input or picture, this probability will give you whether this is tiger or cat. So this probability vector probably give you many different animals, and each number output of this vector will give you the probability of each animal. You can give many different type of pictures, and this deep neural network may determine what has the best probability. And if you show them picture, it will give the input and output will be obtained. And during the training process, this output will be compared to your target real value. If let's assume this picture is tiger, y dash means tiger. So y should be equal to 1 actually for the case of tiger. But if there is some difference, we define cost function. So we iterate this training process until this cost function is becoming to 0. When we are doing this optimization process, optimization means that we are fitting this y weight and bias to fit into the real distribution of this output function. We continue this iteration until this cost is becoming to 0. And then gradually we approach from initial point to the optimal point. To do that task, we usually use the gradient descent method. Probably on Wednesday and next week, we're gonna spend a day to talk about gradient descent method. Now, let's talk about the connection of perceptron. This is the case of where input layer has node number 3. We only have one hidden layer, and node number is 3. We have one output layer, that's node number is 2. And then the connection from a node to input vector, node to hidden layer can be described by a weight number. And this group of weight number can be represented by a matrix, a weight matrix. In the same way, we have connections from hidden layer to output layer. We can also define the weight matrix W dash. So this matrix, weight matrix that connects each layer to next layer will be the key element to describe the connection from one layer to next layer. So output of each layer can be described by vectors, input vector, hidden vector, and output vector. Let me describe the connection of this output vectors with this matrix W. That is what we have done in this page. So if we have W vector and W dash vector, W vector has 3 by 3 matrix, while W dash vector has 3 by 2 vectors. And then by multiplying the input vector with the W matrix, that will give us this weighted sum. That is gonna become our input of sigmoid function, and output of this sigmoid function will be H0, H1, and H2. That is the hidden layer output. Again, this hidden layer output will become input of next layer, next activation function and perceptron. And oh, this is a mistake. It's good to have eraser in this iPad. So this hidden layer output becomes the input of next layer, and that is multiplied with this W dash matrix, that it becomes the input of this sigmoid function, and this sigmoid function output will be the final output of deep neural network. Sometimes mathematics is very easier to make some description. Let me give you some case. So this is the mathematical description of Foward propagation. Here, this is the bias of the bias at this connection from input layer to hidden layer. And this is the W connection matrix. And this is the input vector. This G describes a sigmoid function. This H dot also is the weighted weight matrix W dash. It describes the connection from hidden layer to output layer. This is the bias to make a connection from hidden layer to output layer. This H is the hidden layer output vector. And finally, this Y is the output vector. So far in this class, I was talking about the basic structure of perceptron. Then I described the connections in deep neural network. In third page, I described the connection from input, hidden, and output layer using this mathematics, the matrix formalism and sigmoid function. And at the final page, I described this whole Foward propagation using very simple mathematical formula. In this page, I would like to give you the whole structure of the deep neural network. In the previous page, I was giving you some examples of very small size case with a three layer, one input layer, one hidden layer, and one output layer. Now let's talk about some general case. I would like to give you idea on what is the general structure of deep neural network. Let's assume that I have P11 perceptron and we have up to P1 perceptron and number of node is n. Then we have input x1, x2, and xn. As I mentioned you many times, this n could be million or billion numbers. So in generally this deep neural network has many number of perceptron in a layer. Also, I'm assuming that we have I in a inner layer. Let's assume we have many number of inner layers, and then it has output layer. So in this previous slide, we had only three input and two uh, output vector, output numbers, and we have one hidden layer. One hidden layer has three node number. Now, in general case, we have n input. So the vector size is n, and the number of hidden layer could be many. Here I assume we just put I, and the number of nodes in inner layer is m. I assume that, and at the final case layer we have output layer, number of nodes there are n. That's assuming this is more general case. Of course, as I mentioned before, it is all connected, and each perceptron has activation function. Output of activation function will be propagated through this during the training process, and this calculation process from input to the output of this deep neural network is called forward propagation. And as I said before, we can define cost function using y and y dash. Usually we compare the real number, target number, and our output. And if the number is not the same, we still have some cost. And we update W and B using cost function. That is called backward propagation. And this cost function can be described by in the previous slide, I was talking about single perceptron. Single. This is the case of single perceptron. Single perceptron. Now that is becoming a unit element in this deep neural network. They are still connected, and there are many number of nodes and layers, and they are all connected. When you put the input vector, for example, picture of tiger and cats or whatever, that will become an input, and then you will get the output Y. That is called for the propagation. However, if your output and real number will have some certain differences, that is defined by cost function. And later on, this is very simplified cost function, but later on we will give you some more idea about the complicated cost functions such as softmax and entropy function. But for the simplicity of discussions, I will define some very simple cost function. This cost function, if you have the same number of output with your target number, that is becoming to 0. If that is not becoming to 0, you update the bias and weight using this cost function, and those process is called backward propagation. Now, okay, this is the, later on I will give you more idea about the deep neural network. Let's assume that this is deep neural network 1, but later we can combine many different type of deep neural network together to complete very complicated deep neural network. For the case of transformer learning or GPT-3, the configuration of deep neural network is much more complicated. But still, this kind of deep neural network block is also a kind of a building block of complicated deep neural network. So, my iPad, okay. This perceptron is becoming a building block of deep neural network. This single deep neural network become a building block of complicated deep neural network. These deep neural networks will be connected in series and parallel. There are many different configurations. But if the complexity of deep neural network is becoming higher and higher, forward propagation and backward propagation process will be more complicated, and we may need more computing powers, and it takes more power consumption, and sometimes your computer system takes too much power. That is the big concern. But still, at this moment, I want to emphasize that this deep neural network is a really basic building block. So far, I was talking about some various type of activation functions. At this moment, I would like to give you a few examples. This is the linear type of function. Linear. At this moment, I would like to spend a little bit of time to talk about the activation functions. There could be 100 types of different activation functions to be used in perceptron. Uh, at this moment, I would like to give you very simple cases. First one is the linear, just input is going out through this perceptron, and that function can be described by G. The derivative of this linear function is becoming 1. Why do I'm talking about the derivative? Because this derivative is later we will be used to gradient descent process. During the back propagation and optimization process, we're gonna use this gradient of activation function. Probably next on Wednesday, I'm gonna talk more very deeply into the meaning of this derivative and gradient descent and backward propagation. Second type of function is logistic function. In other words, that is called sigmoid function. As I mentioned before, this has this kind of shape, very smooth function, and we can obtain the derivative using so derivative of this sigmoid function is easily obtained having the value of itself multiplied by 1 by j. So differentiation, it has very easy differentiation. So it has very smooth, beautiful function. Sometimes this differentiation and easy differentiation is very useful for backward propagation because we're gonna use the differentiation process many times. Sometimes also we're gonna use the tangent hyperbolic function that is also described by this formula. It has the -1 to 1. So sometimes depending on your applications and experience, you can choose different type of activation function. And finally, at the final moment of developing your process, you can find out what is the best activation function in your case. I think in order to be able to be good AI engineer or machine learning engineer, you should be able to have good mathematics background, and also you need to have a good software background, and also you need to know computer architecture, and you also have to understand integrate circuit such as GPU and DRAM. So in order to be, this will with this, if you add algorithm, AI algorithm, I think you become AI expert. So this is really a unique area. AI, if you want to become an AI expert, just simply you know very well about the AI algorithm doesn't mean much. You should be able to have basics of AI algorithm. In addition to that, you have to have very good mathematics background, software coding capability, and also you have to understand computer architecture, and also you have to understand what is the basic principles of GPU and DRAM and that kind of stuff. So it takes some time and experience to become AI expert. Now I would like to talk about the mathematical background. What type of mathematics do you need to have? I think first you have to have some background of statistics. Why do we need to have some background of statistics? Because in order to have a good AI programming, you have to should have a very good amount of data and high quality data. Data selection, during the data selection process, you have to have very good statistics background. And second, background of mathematics for machine learning is calculus. Especially in the partial, you have to understand partial differentiation and vector derivative. So especially this calculus is needed during the backpropagation. To find an optimal solution, during this training process, if you find the optimal W and B as fast as possible and efficiently, you have to understand this optimal operations, and in most cases you are using the deep calculus differentiation. Also, you have to understand the linear algebra. A lot of matrix calculation and matrix and the vector operations are involved during the training and inference process of machine learning. So you have to have basic. Also, at the end of this month, I'm going to talk about a lot about the RNN process and LSTM and backpropagation. Then the matrix calculation is very complicated. So you have to figure out what's the meaning of matrix and vector. Also, you have to have some background of probability, especially during the reinforcement learning. You have to have idea about this kind of parameters. At the end of this semester, you will understand what this means, that this is usually D word, and this is the probability. To find the best solution during the reinforcement learning, you have to be able to calculate the probability of each action. Also, you should be able to calculate the reward of your action. And in those cases, I think we need to have some background of probability. I think the most basic fundamentals of machine learning is, I think, mathematics. So in some case, sometimes if I have a chance to talk with the undergraduate student or freshman student, I would ask him to take mathematical course as much as possible, and probably a little bit about computer software. And then they can learn about machine learning algorithm in graduate courses. And then he became really strong. This is the end of my second class today. I started with the perceptron and what's the meaning of perceptron and basic structures, and then I derived some mathematical and graphical formalism of perceptron connections, and this page is the graphical description of perceptron connections. And then also we define the input vector, hidden vectors, and output vectors. And then I developed the mathematical relationship between each output vectors using the matrix calculations and sigmoid function. And this is very simplified mathematical description for the propagation. And then in the previous case, I was showing some example of very simplified deep neural network, and I showed you the diagram to give you an idea about the general structures of DNN. And this DNN, multiple DNN will be combined together to make a very complicated DNN. So this DNN could be be connected in series and in parallel to complete a machine learning network. And the data process in the forward direction is called forward propagation. That is the calculation of output. By comparing your output and the real number, you can define cost function, and then you can update weight and bias using this cost function. That is called backward propagation. And briefly, I was talking about the many different types of activation function. One important property of the activation function is differentiation. Easy differentiation is very important because easy differentiation means we can fastly achieve to the optimal point of the weight numbers. That means that we can complete the training process, forward propagation, backward propagation as fast as possible. That is very important for real-time AI machine. Now, at the last moment of my class, I was talking about the background. What is the needed background or capability to become an AI expert? First thing, I think I believe the basic building block and very most important background of AI expert is mathematics. I think that is number one. Number two is software and computer expertise. And third one is a little bit about integrated circuit background. And third background is the machine learning algorithm. Now, in this class, I'm going to mostly talk about machine learning algorithms. Especially in the mathematics, I think that 4 different areas are needed to make an AI expert. First, during the data selection process, we need to have a very good statistics background. And we also need to have a very good calculus background because we have to understand partial derivatives of cost functions and activation function. Those are needed to develop backward propagation. And also we have to have very good understanding of algebra. Algebra is the most beautiful mathematics in undergraduate courses. And we should be able to understand the property of matrix, inverse matrix, and unitary matrix, and many understanding of matrix will help to develop new model of machine learning. Also, we should be able to understand three-dimensional or multi-dimensional vector operation. We have to have that kind of imaginations. At last mathematical capability we need is probability, especially during the reinforcement learning. We have to find the best strategy and best value functions. By using those reinforcement learning, we can win the games, or we can have best staff investment, or we can find best engineering solution. During the reinforcement learning process, and especially in Bellman process, we have to have some probability functions. We should be able to calculate probability to find the best policies. I think these all are the mathematics that are needed to build or to become a good AI expert. Thank you for your kind attention. In this class, I'm trying to use lecture method using the writing and drawings and like a blackboard. And so I hope this is good for you, and I will keep continuing this type of classing method. Thank you for your kind attention. See you on Wednesday.